Hello. This video includes information on nomenclature, which means writing formulas and names for compounds.
And we're going to essentially take the compounds and kind of subdivide them into different categories because they all have their own little ways of naming them. So the first ones we're going to look at are what we're going to call ionic compounds number one. Okay, sometimes they're called simple salts. Okay, and when we talk about these simple salts, they are binary ionic compounds. Let's kind of break that down for a second. Bi means two. So we're looking at compounds that have two types of atoms in them. And the ionic means that they're being held together by ionic bonds. And we know that ionic bonds are formed by the transfer of electrons and the forming of positive and negative ions. And for these ions, they're what are called invariant ions. The metals are invariant. That means that there's only one possible type of ion they can form. Okay, when we go to name these types of compounds, they're going to essentially have a first name and a last name, kind of like you do. Okay, so the first name that's given is the name of the cation. Okay, remember the cation is the positive ion. Cats have paws. Cations are positive. So this is the positive ion. Okay, and then the name of the negative ion. But the negative ion, the ending will be IDE for its suffix. So let's look at some examples. Okay, NaCl. Well, it's binary because it's only made up of sodium and chlorine. Okay, it's ionic because sodium is a metal with a very low electronegativity and low ionization energy, whereas chlorine is a nonmetal and has a very high electronegativity and a very high ionization energy. So there's a transfer of electrons and there's an ionic bond here. Na is sodium. Cl is chlorine, but we're going to drop the ending and make it IDE. So NaCl is sodium chloride. Okay, CaF2. Okay, Ca is calcium. We don't do anything to the cation name. It's the name of the element. F is fluorine. We're going to make that fluoride. And the fact that there's a 2 here has nothing to do with the way we're going to name it. We're going to talk about where that 2 comes from. So let's say we have Al2O3. Okay, for simple binary ionic compounds, the subscripts have nothing to do with their names. Okay, so what would the name of this be? And then we've got AgCl. What would that name be? And then we've got Ag2S. What would that be? Okay, good. I agree. The first one's aluminum oxide. Good. Yep, I agree that the second one is silver chloride. Good. And what would the last one be? We have a couple of them in there. Silver sulfide, right. Oh, I had one more. ZNO, what do we think that one is? Zinc oxide, good. Okay, they got a first name and a last name. The cation is just whatever the name of the element is. The anion, we just drop the ending and put IDE, and the subscripts have nothing to do with the way they name them. So we want to know, well, where do those subscripts come from? Okay, well, they have to do with the charges on the ions. And that's something that, we've already talked a little bit about. And even when we talked about the ratio of ions in a compound to make them neutral, we've gone through. So let's just review that real quick. Okay, all of the alkali metals will have a charge of +1. All of the alkaline earth metals have a charge of +2. All the elements in group 3 are +3. Okay, then if we go over on this side, these are 0. The noble gases don't form ions. 1 over, okay, those are your halogens. They're -1. 2 over, okay, these are your chalcogens. They're -2. And 3 over is -3. Okay, we don't have to memorize what those are. We just have to know where they are on the periodic table. Now, there's a couple that we have to memorize. Silver always forms a +1. Okay, not necessarily the same as, elements that are around it. So we just have to know that silver is a +1. Zinc and cadmium are always a +2. Okay, so as long as we know +1, +2, +3, -1, -2, -3, and silver is a +1 and zinc and cadmium are +2, that's what we need to know. Okay? Now, what do we use them for? Well, we use them for writing formulas for compounds. So if we were to look at potassium on the periodic table, it's an alkali metal. It has a +1 charge when it forms an ion. When we look at iodine, it's a halogen, it's going to have a -1 charge. And we talked about how we want to make that compound a neutral compound. We just crisscross the numbers. So these two ions would form the formula Ki. The one from the potassium would come down here, and the one from the iodide would come down here. And we would call it then potassium iodide. So crisscrossing the numbers, let's see if we have a potassium ion combined with an oxide ion. What would the formula be and what would the name be? All right, so let's see how we did. Potassium has a charge of +1. Now, I did write it here, but you can figure this out on the periodic table, right? So it's an alkali metal. That 1 comes down and it's the subscript after the oxygen. And we assume 1s, we don't write them. The 2 from the oxygen is going to come down here. We're not going to put charges, though, when we write subscripts. So we need 2 potassiums and 1 oxygen to make a neutral compound. And our compound would then be called potassium oxide. Okay, so let's see if we can do the next one. If we've got potassium and nitrogen, what would we have? Yep, K3N, and we would call it potassium nitride. Good. All right, let's try this one here. Calcium and iodine. What would the formula be and what would the compound be called? Agreed. Okay. CaI2, calcium iodide. All right, so let's try this one. Potassium or calcium and oxygen. This is a little bit tricky. Think about what we talked about a couple classes ago. Excellent. +2, -2, but we want to simplify them. We only need 1 calcium and 1 oxide to make a neutral compound. And our formula is calcium oxide. Okay, calcium and nitrogen, what would the compound be? Good, Ca3N2, calcium nitride. All right, let's do Al and I. Yep, and a kind of funky looking, but Ali3, aluminum iodide. Good. Okay, how about the aluminum and the oxygen? Yep, Al2O3, right, aluminum oxide. How about the aluminum and the nitrogen? Excellent. Aln. We crisscross those 3s, but then we're going to simplify them. We only need 1 of each. So aluminum nitride. All right, so now I'm going to make it a little bit more challenging. Instead of giving you the charges and asking you to write the formulas, I'm going to give you the names. You need to use your periodic table, figure out what the charges are, and then write the formula for those compounds. I'll give you a couple minutes to do that, and then we'll go over it, and then we'll take a break for just a couple minutes, and then we'll come back. little bit more challenging now, probably because I'm not giving you the charges. So you're going to have to figure out the charges first, then crisscross them and make sure they're the simplest form. And when you're done, just so that I kind of get a ballpark for where you are and how long it's going to take. Once you do magnesium sulfide, you put the answers in the chat just for the magnesium sulfide. I'll know that you're done, and then we can go over them real quick. I don't want to go over them until you get a chance to try and do them on your own. Magnesium's MgS. Sorry, where'd I get that? I gave you the answer. Magnesium's Mg. Oops. Yep, there you go. Oh, you guys are going so quick. It's awesome. It's okay. All right, so we got a good handful done. Let's see how we did. So silver nitride would be Ag3N. Zinc phosphide would be Zn3P2. Cesium oxide would be CS2O. Okay, next column, aluminum bromide would be AlBr3. Barium fluoride is BaF2. And magnesium sulfide is MgS. How do we do? Anybody have any questions on them? A little easier than hybridized orbitals, right? All right, so this is what we're going to do. We're going to spend maybe 4 or 5 minutes, okay, max, because we still have other things we need to get through today. 4 or 5 minutes max. We'll take a quick break, get up, stretch a little bit, go to the bathroom, get yourself something to drink, and let's start up again about, I don't know, 7:13, 14, something like that. Okay, give you a couple minutes just to take a breath. All right, see you in a minute. Another minute or two and we'll get ourselves started back up again. All right, so let's get ourselves started back up. So the next thing we're going to do is talk about another type of nomenclature for what we're going to classify as ionic compounds group 2. And these are ones that contain what are called polyatomic ions. Okay, so polyatomic ions are ions that are made of more than one atom. Poly means many. Okay, they have a charge and they're made up of more than one atom. Okay, so this kind of summarizes the polyatomic ions that we're going to be using. So if we were to look here, I'm not going to go through all of them, but if we were to look here, dihydrogen phosphate is H2PO4 minus 1. Okay, so it has 2 hydrogens, 1 phosphorus, 4 oxygens, and the overall charge on this polyatomic ion is minus 1. And all of these in here, polyatomic ions with a minus 1 charge. Now, next two, we've got nitrate and nitrite. Okay, well, they look very similar. They both contain nitrogen and oxygen. Okay, the suffix ate in a polyatomic ion tells us we're looking at the more common form of that ion. So nitrate is NO3 minus 1. Okay, 1 nitrogen, 3 oxygens, an overall charge of minus 1. The ite form has 1 less oxygen than the ate form. So if nitrate is NO3 minus 1, nitrite just has 1 less oxygen. Okay, if we were to look down here, if we look at chlorate, okay, it's ClO3 minus 1. Chlorite has 1 less oxygen, ClO2 minus 1. Now, the prefix per means 1 more oxygen. So if chlorate is ClO3 minus 1, perchlorate just has 1 more oxygen. And hypochlorite, hypo means under. So hypo would have 1 less oxygen than the ite form. So if chlorite was ClO2, hypochlorite is ClO. They all have the same charge though, minus 1. I'm just trying to give you, little things that you can see pattern-wise with these. But all of these ions in this first column, they all have a minus 1 charge. Okay, the ones that are listed in this second column, they all have a minus 2 charge. Let's look at this one, sulfate and sulfite. Okay, sulfate is SO4 with a minus 2 charge. Sulfite just has 1 less oxygen, so SO3 with a minus 2 charge. Okay, minus 3. Okay, phosphate is PO4 with a minus 3. Ite just has 1 less oxygen, so PO3 minus 3. Now, of all of these that are listed here, these are the 2 common polyatomic ions that have a positive charge. So ammonium has 1 nitrogen, 4 hydrogens, and the overall charge is plus 1. If we were to look at mercury, this is a little unusual. Okay, it's a polyatomic ion because it has 2 mercury atoms in it. The overall charge on this polyatomic ion is plus 2. We're going to call it mercury 1 though, because if we've got 2 mercury atoms with an overall charge of +2, one of them would have a charge of +1. So that's where this 1 comes from. Okay, it doesn't exist that way though. It exists as a polyatomic ion. So these are some polyatomic ions. Now we're going to incorporate them into how to write formulas. So let's say that we have NaNO3. Okay, well, Na is sodium. Okay, that's a monatomic ion, or it's made of only one type of atom. NO3 on the polyatomic ion sheet, that's nitrate. So this whole compound is sodium nitrate. Okay, if we were to look at this one, again, we want to look and see that it's got a kind of first name and a last name. Okay, Ca is calcium, CO3 is polyatomic. We're looking at calcium carbonate. Okay, K3PO4, potassium phosphate. SR3 PO3 is strontium phosphite. Now think about this. Strontium's an alkaline earth metal. It has a charge of +2. That's where this 2 comes from. Phosphite has a charge of -3. That's where this 3 comes from. So we're still crisscrossing the numbers like we did for the simpler binary ionic compounds. It's just a little bit more complicated because it involves polyatomic ions. So K2SO4, potassium sulfate. Now, this one kind of looks like it's a whole bunch of different things. This is hydrogen sulfate. So it's sodium hydrogen sulfate. Okay, this one here is sodium oxalate. And I want to point something out here. Okay, the charge on sodium is a +1. Okay, so we've got 1 oxalate. The charge on oxalate's a -2, so that's where this 2 comes from. Now look at this. There's a 2, a 2, and a 4. We're not going to be simplifying this because oxalate is C2O4. We're not simplifying anything in the polyatomic ion itself. We have 2 sodiums and we have 1 oxalate. So again, if we were to, kind of look at what happens with these, if we were to look at aluminum, okay, it's got a +3 charge. If we were to look at sulfite, it has a -2 charge. Again, we're going to take the 3 from the aluminum and drop it down as a subscript. We're going to take the 2 from the sulfite and drop it down as a subscript. So our formula would be Al2SO33. Again, the charge on the aluminum comes down here. The charge from the sulfite comes down here. And if we look, each aluminum is a +3 and there are 2 of them. Okay, that gives us a +6. Each sulfite is a -2 and there are 3 of them. That gives us a -6. Compounds are always neutral. And they're always going to be neutral if we crisscross those numbers. Oh, yeah, I agree. Per and hyper, yep. All right. So let's do this one, ammonium acetate. Okay, you can go back a couple of slides and see what ammonium is. Okay, if not, I'll tell you. Ammonium is NH4 with a +1 charge. And you can look on a couple slides before it what acetate is. Acetate is C2H3O2, and it's got a -1 charge. Okay, so see if you can figure out what the formula for ammonium acetate would be. Okay, so all we're doing is here's our ammonium, NH4. Here's our acetate, C2H3O2. We're just crisscrossing the ones. Okay, we don't necessarily even need to write them there. Okay, let's say we have potassium permanganate. Okay, potassium is a K with a +1. We find that off the periodic table. Permanganate's polyatomic. I'll tell you it's MnO4 with a -1 charge. So what would your formula be? So KMnO4. All right, how about zinc oxalate? Okay, zinc is Zn. We just have to know that it's got a charge of +2. Oxalate is C2O4 with a -2 charge. So we've got a +2 charge and a -2 charge. Think about what we're going to do with those numbers when we go to write our formula. Okay, so the 2's get simplified. Zinc oxalate is ZnC2O4. All right, potassium nitrate. Okay, we know what potassium is, plus we did it up here. Nitrate is NO3 with a -1. Okay, so KNO3. Okay, how about potassium nitrite? Okay, think about the pattern I told you about the 8 form of a polyatomic ion relative to the 8 form. So if nitrate is NO3, we should be able to figure out what nitrite is and see if we can write the formula for potassium nitrite and put that in the chat. Let me see how you're doing. Good. Okay. Potassium is K with a +1. Nitrite would be NO2 with a -1. So KNO2. Okay. One more. This is a little bit of a trick. Okay. It's not polyatomic. It ends in IDE. Okay. That means it's like the first group we talked about. Okay. Think about what nitride would have to be. It's a nitrogen ion. Look on your periodic table, see if you can figure out what the charge on a nitride ion would be. And then see if you can write the formula for potassium nitride. Agreed, excellent. Okay, since potassium is an alkali metal, it has a +1 charge, so that 1 comes down here. The nitrogen is in group 5, so it's got a -3 charge, so that 3 is going to come down here. Excellent. IDE, in almost all instances, means we're talking about a monatomic ion. Okay, there's a couple of exceptions. Hydroxide and cyanide are polyatomic, but they end in IDE. Most of them end in ATE or ITE, though. All right, so now let's look at the next kind of category of nomenclature. We're going to call them ionic compounds type 3. Okay, these are ones whose cation is from a metal that has more than one possible charge. Okay, they're called variant metal ions. So sometimes, especially in the transition metal section, there are atoms that can form more than one possible charge. Okay, so as an example, chromium can form an ion with a +2 charge, but it can also form an ion with a +3 charge. Okay, copper can form an ion with a +1 charge, but it can also form an ion with a +2 charge. So how do we know which one we're dealing with? Okay, well, we're going to use Roman numerals to stand for the charges on the ions so we can differentiate them. So as an example, if we have iron 2 chloride, this is actually almost easier when they're not variant metals, because this tells us the charge. Okay, iron is Fe, The charge on the iron is a +2, tells us right here, because iron can be 2 or 3. It has to tell us which one it is. Okay. And chloride's a -1. Once we figure that out, we just crisscross and write the formulas. Okay, so iron 3 chloride is FeCl2. All right, so what would lead 2 sulfide be? Okay, lead is Pb. This tells us what the charge is. You have to look up on the periodic table and figure out what the charge on sulfide would be. Good. Okay, lead's a +2, sulfide's a -2. Those 2's are going to simplify. Good. All right, how about lead 4 oxide? Well, this kind of gives us everything we need to know about the lead. Okay, Pb +4. Got to look up what oxide is. Crisscross, and for ionic compounds, we want those subscripts to be the simplest ratio. What do you think lead 4 oxide is? Good. Okay. +4 -2 gets simplified. PbO2. Good. Tin 2 nitrate. So now we're combining 2 things together. This is a variant metal ion. Okay, tin is Sn. Okay, tells us what the charge is. This is polyatomic. Okay, nitrate is NO3 -1, if you don't want to look back a couple of slides. Okay, NO3 -1. So we have to be a little bit more careful with this one. Okay, it's the first time actually we've seen something like this, I think. We want to show that there are 2 nitrates. So we're going to put parentheses around the nitrate so that it shows we have 2 of them. This 2 goes to everything inside the parentheses. So we've got 1 tin and we've got 2 nitrates in our formula. All right, how about copper 2 sulfate? Okay, sulfate is SO4 -2. SO4 -2. So what would copper 2 sulfate be? All right, so the 2 from the copper comes down here. The 2 from the sulfate comes down here, but we can simplify those 2's. Okay, they're always going to be the simplest ratio. I don't know what happened to the, oh, we lost it. This should say copper 1 oxide. I don't know where that went. So the copper is a +1. The oxide is a -2. Okay, so this kind of combines together a couple of different things. So, we're actually going to skip that. I'm going to make that the warm up for Monday. Let's make that the warm up for Monday. All right. So let's go on to the next type of nomenclature. We're going to look now at covalently bonded compounds, okay, which are called molecules. So we talked about a couple of different ways that we can write formulas for ionically bonded compounds. Now we're going to look at covalently bonded compounds. So now molecules. So now we're looking at sharing pairs of electrons, right? And their ratios can vary a lot when we look at these kinds of compounds. So we're going to use prefixes to define how many of each type of atom we have. So when we go to name these types of compounds, we're going to use a prefix and then the name of the first atom that's there, and then a prefix and the name for the second atom that's there, but the ending on the second one is going to be IDE. So what are the prefixes we're going to use? Okay, let me move this over here a little bit. So our prefixes, one is mono. Okay, now I put a little thing down here. We assume mono in the first name. Okay, so we don't write mono in the first name, but if there's one of the second element, then we would use mono. 2 is di. 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. And a lot of those are probably familiar, maybe from like geometry classes and things like that. And we're going to be using those prefixes. So let's look at some examples. Okay, CO. Well, first of all, they are 2 nonmetals. Okay, 2 things that are on the right-hand side of the periodic table. If you see that, this is the kind of compound we're looking at. Okay, if both of the atoms that are in the compound are nonmetals, we're using prefixes in the name. Okay, we've got carbon and oxygen. There's 1 carbon and there's 1 oxygen. The prefix for 1 is mono, but we don't use the mono in the first name. We just drop that. So we don't say monocarbon. It would just be carbon monoxide. 1 carbon, 1 oxygen. Okay, CS2, carbon disulfide. Okay, 1 carbon, again, that mono is assumed in the first name. Di means we've got 2, and we've got the prefix IDE. So, dichlorine penta or pentoxide. Okay, we're actually going to get rid of a letter in there in a minute. Okay, iodine trichloride and xenon tetrafluoride. And just because it's awkward, if we have like 2 O's together, like we don't write, I don't know if there's, we don't write monooxide. Okay, we're just going to kind of combine them together and say monoxide. And if we have an A and an O in there, we're going to kind of shorthand that and not say pentaoxide. We're just going to say pentoxide. Okay, just to kind of make it a little bit easier. So we have a couple practice problems here. Okay, they are all covalent molecules. Okay, both of the atoms that are in the compound or the molecule are nonmetals, with the exception of this one down here. This should not be on that list. We'll cross it out in a second. Silver oxide is not part of this. So I apologize. That shouldn't be in there. So for the first 5, do those. They are all non-metals. That's why there are prefixes in there. There's no crisscrossing. If you see prefixes, there's no crisscrossing. Okay, if you don't see prefixes, there is crisscrossing. So write the formulas for these, and they're pretty literal. And then write the names for these. And then we'll go over them. So carbon tetrachloride is CCl4. Sulfur hexafluoride is SF6. Dinitrogen tetroxide is N2O4. Now, for covalent molecules, we don't simplify them. Okay, ionic ones we do. Covalent ones, this is the way this molecule is found in nature. We're not going to want to simplify it. A xenon difluoride is XeF2. Sulfur dioxide is SO2. Okay, and these are all 2 nonmetals combined together in a molecule. That's why we're using prefixes. Okay, this last one here doesn't fit with the pattern. This is a metal and a nonmetal. This is ionic. Okay, silver's a +1, oxygen's a -2. So this, you could even just cross this out because it doesn't fit with the pattern, nor does the last one on the next one. Okay, so this is maybe here just to see that this is different than all of these. If it's a metal and a non-metal, we're figuring out the charges and crisscrossing them. If it's 2 nonmetals, we're using the prefixes, and it literally tells us what we have. Okay, questions on that first column, and then we'll go on to the second column. All right, let's look at the second column. Okay, nitrogen trioxide. Now, here's something. This looks a lot like a nitrate ion. The difference is this doesn't have a charge. So this is not an ion. It's got nitrogen and oxygen in it that are both two nonmetals. So this is a covalent molecule, nitrogen trioxide. Okay, carbon disulfide, iodine trichloride, sulfur tetrafluoride, iodine tribromide. Okay, notice they all end in IDE. Okay, the first name does not. We just leave the name the same as the name of the element. The last one is IDE, and we use the prefixes to tell us how many. Now, this one here, aluminum is a metal, and chlorine is a nonmetal. This is not a covalent molecule. This is ionic. So we're not going to use prefixes when we go to name ionic compounds. So you might want, if you wrote these all down, circle this last one here and circle this last one here. They are not the same as the ones up on top. All right, last type of nomenclature we need to go through is how we name acids, because they have their own little special rules. And one thing we need to know for now is that all acids start with a hydrogen ion. Okay, that's what defines them as an acid. And we essentially have two types of acids. Okay, the first type are binary acids, which means they have hydrogen and some monatomic ion for its anion. So when we go to name it, we're going to have specific rules. Okay, if it's a gas, we name it like it's an ionic compound. So hydrogen fluoride gas or hydrogen chloride gas. Okay. But if it's aqueous, that's what makes it an acid. When we go to name binary acids, ones that only have two types of atoms in them, the prefix is hydro, the suffix is ic. So this is hydrofluoric acid. This is hydrochloric acid. The only thing that changes is what the stem is, what the root is. Okay, this is hydrocyanic acid because CN is cyanide. So hydrocyanic acid or hydrosulfuric acid. Now, if the acid is what we call an oxyacid, that means it's an acid that contains oxygen. It would have a polyatomic ion in it as its negative ion. And what we would have to know is what's the polyatomic ion and what's the ending on that ion. If the ion ends in 8, we're going to drop the ending off of that and replace it with ic. If the ion in the oxyacid ends in ite, we're going to drop that and use OUS. So, examples. HNO3. Okay, well, ooh, there's a typo there. HNO3. Well, it's an acid because it has hydrogen in it. Notice they all have hydrogen in them. NO3 is polyatomic. It contains oxygen. When we look it up, this is nitrate. So we're going to drop off the 8 and we're going to put ic as the end. It shouldn't be nitric ic. Or take off one of those ics. Okay, so nitric acid. Notice there's no hydro in front. Okay, if we have HNO2, it's an acid because it has hydrogen in it. NO2 is nitrite. Ite goes to us. So this is nitrous acid. Okay, this is sulfate. 8 goes to ic, so sulfuric acid. This is sulfite. Ite goes to us, so sulfurous acid. This is phosphate. Ate goes to ick, so this is phosphoric acid. So let's look at a couple of examples. So HBr is hydrobromic acid. HCl is hydrochloric acid. And if we look at those two, they're both binary acids. That's why the hydro is there. If we look at HClO, okay, now it's got oxygen in it, so we don't want to write hydro. ClO is hypochlorite. Ite goes to us, so hypochlorous acid. That's not hydro, hypochlorous acid. Okay, this would be chlorous acid since it's chlorite. This would be chloric acid because this is chlorate. This would be perchloric acid because ClO4 is perchlorate. And this would be oxalic acid because C2O4 is oxalate. Now, the last thing that's there was kind of a trick. HOH, that's really H2O. Okay, H2O is water. Okay, just stick it in there. So let's look at the other side. So carbonic acid, it goes back to 8. We need carbonate in our formula. Carbonate is CO3. It has a -2 charge, so that 2 would come down here. Hydrogen's a +1. So H2CO3. Hydrofluoric acid, well, since it's got hydro in it, it's a binary acid, so the anion is just fluorine. Okay, so +1, -1. Okay, hydrogen fluorine gas, okay, how do we know it's a gas? Because it's not named as an acid, so we put the little gas here. Phosphorus acid, us goes to ite, so we need phosphite. Phosphite is PO3 -3. So the -3 charge on the phosphite comes down here, and the +1 from the hydrogen would come down here. Hydrochloric acid, okay? Hydro means it's binary, okay? Chlor means we've got chlorine, +1, -1. Nitric acid, so we would need nitrate, which is NO3, +1, -1. Sulfurous acid means we need sulfite, which is SO3. That has a -2 charge. So the 2 would come down here, and the 1 from the hydrogen would drop down here. And if you want some more practice, there is actually a pretty good website that gives you the opportunity to practice naming and writing formulas for acids. And again, that's on your PowerPoint, so you can just kind of click on that if you need a little bit more practice on that.